Chapter 10, Section 3 is about composite figures. So by the end of this lesson, you should be able to use the area addition postulate to find areas of composite figures, and then use composite figures to estimate areas of irregular shapes. So remember, the area addition postulate said that the area of a shape is the sum of all of the areas of a shape. So when you get something that looks like this, we can find each of these individual areas, add them up, and that will be the total area of the shape that we were given. So a composite figure is made up of simple shapes such as triangles, rectangles, trapezoids, and circles. To find the area of a composite figure, find the areas of the simple shape, and then use the area addition postulate. So this first one here looks kind of messy, but the first thing I notice is they tell us that lines are parallel. And if we look at these lines that they tell us are parallel, these ones and these ones, this makes a nice pretty parallelogram. And because this is a parallelogram, we can use the formula that we know for area, that's just base times height. And remember, the base has to be one of the side lengths, and the height has to make a right angle. And lucky for us, they give us this for the base, and this is our height. So the area of this shape here is just 8 times 5, or 40 feet squared. Now this other shape we can see is a nice triangle. And remember, the area for a triangle is 1/2 base times height. And if you look, they gave us a base and they gave us a height. It also has to form a nice 90-degree angle. So here's base, here's height. So area is 1/2 5 times 10, so half of 50 is 25 feet squared. So the area of this entire figure here, that's what I really want to know, is our parallelogram plus our triangle. So we end up with 65 feet squared. Not too bad. Let's try one that's a little different. Since we want this shaded area and part of it's cut out, we're going to have to subtract instead of like we did here with adding things together. So this original shape that I see is a giant triangle. I know the area of a triangle is 1/2 base times height. And they give us those two pieces of information. This would be the base, and this would be the height. So let's find the area of this entire triangle here without that chunk taken out. So 1/2 times 26 times 18. If you multiply 26 by 1/2, you get 13. Times that by 18, you end up with the whole triangle is 234 feet squared. Now we do not want that entire triangle. We want to take a bite out of this triangle. And anytime you see a shape like this, assume that this is a circle. It's not a whole circle, it's only half of a circle, but we can still use our circle formula. The area of a circle is pi r squared. Since they tell us this whole distance here, that's our diameter. So in order to cut it in half to get our radius, we would get 4.5. And if we do 4.5 squared, we end up with 20.5, or 20.25. And then we want to multiply that by pi. So 20.25 pi is about 63.62 feet squared. So we need to take that 63 square feet out of our entire triangle. So this time, we're going to take these two numbers that we have here and subtract. So we end up with 234 minus that 63.62, and I get 170.38, round to the nearest tenth, so we'll say 0.4 feet squared. And that is the triangle with the bite taken out of it. So the last thing we got to do is talk about irregular shapes. To estimate the area of an irregular shape, you can use a composite figure. So you need to draw a composite figure that resembles the irregular shape, then divide it into simple shapes. So when I look at this, it's really easy to say, okay, this kind of looks like this cut through here, and then that cut through there. And we're losing a little and gaining a little on each of these, so it's going to be a nice estimate. But then this is really easy to find the area of. We can break each one of these into triangles or squares or some variation of that and find the area of each one of them. So that's what we're going to do for this next problem here. So use the composite figure to estimate the shaded area. The grid has squares with a side length of 1 foot. So each one of those squares in there is a foot squared. So when I see these ones here, this is nice and easy for me. Each one of these guys is 1 square foot. And this one up here. And then it kind of gets sketchy. This guy here is about half of a foot squared. And this guy here I'd say is about half of a foot squared. And then this one, we can kind of break up into a triangle. I'm going to say this guy is a half of a foot squared again. And this is half of 2, so I'm going to say that's about 1 foot squared. And that's because I'm not going to count this at all, so that's kind of going to make that like blend out that way. So then when we add all these together, we can see what we have. We have 1, 2, 3, 4, and then we'll make that make 1. So there's 5, 5.5 feet squared. And you can get really into how you're doing this, like with this figure here. You could make this triangle and do 1/2 base, which is 3, times the height, which is 1, and figure out the actual formulas with this. Or you can just stop and think about it. Like this square here would be 2 by 2, so it would have an area of 4. This cuts these two in half, so it would have an area of 1, and so would this. So for these, it's finding nice, easy ways to break this stuff up so that you can find each individual area. So you should be able to use the area addition postulate to find the areas of composite figures, and then do the thing that we just did to estimate some areas. If you have any questions, make sure you write them down and we can go over them in class tomorrow. Have a good night.